Hello everyone, today I'm presenting our work, Fast Fourier Intrinsic Network. This is a collaboration among Tembec University, King's College London, and Czech Technical University in Prague. First, background. We are doing the task intrinsic image decomposition, which is to separate a natural image into its albedo and shading, where albedo is a reflection of scene material, while shading is concerning lighting and scene geometry. The state-of-art works mostly focus on multi-pass structure to solving this problem. Also, they try to add actual loss terms in the neural network to enforce global similarity between their prediction and ground truth. There are also some works they try to learn from auxiliary data to further improve the performance. Right, our motivation is that the image level of details studied in previous works are actually best understood in the spectral domain, where we gave an example of the level of details in the spectral domain using the fast Fourier transform. In terms of this, we propose three contributions: spectral bending, spectral loss, and spectral residue block. These new components are basically to replace the spatial counterparts in the prior works. First, the overview of our fast Fourier intrinsic network, where you can see we have an input image. It is first transformed into the Fourier domain and to create multiple low-pass filtered feature maps. And then they are fed into the spectral residue block for further processing. Eventually, we associate ground truths of spectral bendings such that all the spectral bending maps will be summed up together to predict the final prediction of either albedo or shading. Now let's look at the first component, new component in our work, which is spectral bending. Spectral bending is defined with this equation, where we simply keep the components between certain range in terms of x and y axis in the spectral map. You can see the example here. If we take the lower boundary of the spectral bending are zeros, then they are basically create a series of low-pass filtered feature maps. And if the lower boundary of the spectral bending are non-zeros, they are actually basically represent a different frequency part of the image, and they can be merged together for one complete image. The first case, when the lower boundary are zeros, they are applied at the beginning of the network to create multiple low-pass filtered feature maps. While the second case, for lower boundaries being non-zeros, they are actually used to create ground truths to associate at the end of the network such that the predicted feature maps can be summed up to create the final prediction. While for spectral residue block, it is rather simple. The input and output are in the spatial domain, but the conf weights are parameterized in the spectral domain. While for spectral loss, we use the magnitude of spectral map as it contains the information of image geometry structure in the spatial domain, while discarding the phase part as it is invisible. Our experiment setup. We conduct experiment on different datasets: MPS Intel, MIT Intrinsic, and IIW. The default spectral bands, number of spectral bands is 5, and the number of spectral residue block is 10. And we have the evaluation metric follows previous works, which is listed here. Results shows that our method actually performs the best on the MPS Intel dataset on both scene split and image split setting. While on the MIT Intrinsic dataset, our method also performs the best overall compared to other state-of-the-art. For the IIW dataset, since its ground truth is not dense, it's sparse ground truth, our spectral loss actually cannot apply. But still, you can see our method, it actually performs competitive result to the best performing result before. We have many ablation studies presented in the paper. We gave one example showing the network training convergence for the proposed spectral residue block compared to spatial residue block. And we also have many visualization examples in the paper where you can check them. Conclusion, we propose a fast Fourier intrinsic networks architecture for intrinsic image decomposition, and it differs from existing works in the sense that inference and network training is performed in the spatial domain, and multiscore learning is implemented by spectral banding. Our experiments with 3 popular datasets verify that FNIT achieves state-of-the-art accuracy without accurate training of other parameters. Thank you very much for listening. Welcome to our paper discussion.